Hello everyone, welcome to the first video on this channel. This video will be part of a video series in which I try to give a preparation for university. The bias of those videos is a document, or are two documents by the TU Dresden, a German university, which published in 1988 a document for people who want to study math as preparation. So, since I think this is one of the best documents and preparation which are available right now on the internet, I try to translate it in English and give you some ideas. So, I also have a blog in which I'm going to upload some ChatGPT prompts or AI prompts or whatever, which you just can copy and then give your AI, and it's going to do exercises. I'm going to update those blogs with every new video, and then you just can copy it out, what you learned till then, and you can have a very effective study session. So the first thing all those higher math classes normally starting is at set theory. So those are like the basic ideas which introduce you to the mathematical, to the math world. Let's just make this a bit bigger. So, the first definition of a set is following. A set is a mental summary or well-determined and well-differentiated object of reality or thought. The objects of a set are called elements of a set. We are going to have a look at well-determined and well-differentiated just in a bit. I'm sorry for my English, by the way. So the first is an example. The set of all students in a math class. In this case, the elements of this set would be the students in those math classes. We have, for example, usage of sets if we are talking about numbers. So I hope those sets seems kind of familiar with you. So we first have like n is a set of natural numbers. I guess you all know the sign. It's like this here. So then we have this here, set of all integers. Then Q, set of rational numbers. R, set of real numbers. And C, set of complex numbers. Just to give you an idea why we need sets, and we are going to talk about like set of numbers and number theory as a whole just in the next video, in the next chapter. So let's continue. Let M be a set, then X with the element is an element of M. So X is an element of M as a set. So this sign here is extremely important. So every time you see this just means is an element of something. If we have like this E with a vertical line, then it just means X is not an element of M, or is not an element of something. So example, 7 is an element of all natural numbers. So you know, natural numbers 1, 2, 3, 4, 5, and so on. And -1 is not an element of the natural numbers. This should be, if you know the definition of natural numbers, very obvious. So something like 3/4 is not part of the natural numbers, or square root of something. I'm sorry, square root of, for example, 2. As long as the root will give you a natural number, it is valid. So, characterization of a set. Sets that are frequently appear are assigned specific letters. For example, in math papers you will see this a lot. So the basic letter for a set is M, and here you are seeing that M is defined as x1, so element 1, element 2, element 3, and so on till element n. Characterization of a set M by listing its elements. This is possible. Let's say you have like a set M equals to 1, 2, 3. Then M is clearly there's a clear characterization by just saying M has the elements 1, 2, 3, and that's it. You could say has only the elements of 1, 2, 3. This would be a bit better, but I think the idea is clear. So characterization of a set by listing its elements. Example, oh, there's already an example, I'm sorry. M is defined as 1, 5, 3. Then it's the same thing then as just 3, 5, 1, so you can swap just the elements. In set 3, this will stay the same. Don't make a mistake, because I talked with my sister about this, and my sister made a crucial mistake. So she thought this is nothing else than like in probabilities, where you if you swap the elements, then something completely new will happen. But this isn't the case in set 3. You can swap the elements, so you could say 1, 5, 3, 3, 5, 1, and so on. However, we see already 1 is an element of M, right? We see it right here. However, 0 is obviously not an element of M, because it's not defined in our set right up here. So, of course, this characterization just works if you have finite sets. If you have an infinite set, of course you can't list all the elements, and I mean, you can swap maybe the first numbers, but you can't swap all numbers since you don't know the whole set. So always know it's only possible for finite sets. If you have infinite sets, it gets a little bit deeper and a little bit interesting. So let's go on. Characterization of a set M by specifying the property or properties that determine whether an object is an element of the set or not. So this is defined as X, and then we get something. Let's say, for example, there's an example, but let's say in our set we have like all math students, and from those math students we only want those with blue shirts. So in our set will look like this. Let's go up here. M is equal to, let's say, X with the element of, let's say, MS for math student, and X equals blue shirt. Yeah, this is not correct, but just to get like the idea. So if our X is a math student, if our X is a math student and it is equal to a blue shirt, so our math students got a blue shirt, then it's defined in our set. I think this idea should be clear. Let's go away from the blur of language. Language is always not accurate, so let's have a look to math. So a set A is defined by X is nothing else than X with the element of R. Okay, so we know that our X is a part of the real numbers. In German we would say reelle Zahlen, so I'm always reelle numbers. So I'm always a bit confused. I want to say reelle, but the correct term in English is real numbers. And X has to be smaller than 0. What does this mean? So you could just think, you can pause the video, think a few seconds, but I think this should be quite obvious. Of course, this just means that X is all negative numbers, right? So this is like the definition of the first set of the negative real numbers. So let's go with this. Now you should try to find out what this set definition means. So just pause the video real quick. So this does mean, so if you have a look, X is equals to 2k, and k is defined by 1, 2, 3, and so on, so all natural numbers. So if we say, for example, 1, I'm sorry, 1 times 2 equals to 2. 2 times 2 equals to 4. 3 times 2 equals to 6. So you actually get all positive, all even natural numbers. I wanted to say all positive, but all natural numbers are positive. Therefore, this is just everything, all natural numbers that are even. I mean, the definition of even is that it can be divided by 2 and you still get the natural numbers. I mean, you don't do anything else than this. So, second example. X with the element x is a part of all real numbers and x is bigger 4. Pause the video real quick. So what this means is basic all real numbers that are bigger than 4. Yeah. For example, 4.1 or 4.000001. Yeah. I think this should be clear. I think this is like basic mathematical language, very easy. Seems bit confusing maybe at first because you're not used to it, but always remember, math is about getting as much information as possible in as less symbols as possible. And I mean, you have so much information in like, what is this? 5 symbols. I'm sorry, 7 symbols. In like 7 symbols. Yeah. So, it is also possible to write x with x being bigger than 4 if it's clear that x is part of the real numbers. Yeah, mostly in in books and literature, you will see that it's quite clear that x is a real number, and then you don't have to write x with the element of air. And I'm going to use this term often as well, so I'm not always going to say x is a part of real numbers, but because it can be, it is common sense, therefore you don't have to always write this. But on the other hand, it makes things sometimes a bit more clear, so if you do this, it's not wrong. So, more examples. X, so our solution is x, x squared equals 4. What is the solution for this? Of course, the solution is 2 and minus 2. We see 2 squared is 4 and 2 and minus 2 squared is also 4. So x with the element of x is a part of all real numbers. Here I wrote this again, and x equals minus 1. What is the solution to this? You can pause the video as well. So the solution obviously is m equals this. So it's like an empty set because there are no solutions. Real solutions. If we go to imaginary numbers, because in fact every function with an exponent of 2 has 2 solutions, but this would go too deep into the imaginary numbers. But for real numbers, we know x times 2 x squared is nothing else than no solution. And equals 1 is nothing else than that there is no solution. Yeah, because if we would say 1 or minus 1, it will always be 1 and not minus 1. So there are no solution. And so Zm equals this. Let's go on. Set relations. So set relations are extremely important and maybe the most confusing part of today's video. So if you understand this, you should understand most of the basic set theory, or at least the idea. We need to define the different kinds of relations. If we have 2 sets A and B, and those sets are equal, then we just say A equals B, and the sets A and B are equal if they contain the same elements. So I try to make it here. Let's say A is blue and green is B. A is blue and green is B. We see this is like the same area. If you don't understand like this little drawing, it should be clear if you see the other example. Second definition: if every element of A is also an element of B, the A is called is called subset of B. Yeah, so A is part of B. You also see often like this symbol instead of this. Normally it just means the same. People are just too lazy to write this. So A is called subset of B. We can see this in the drawing. You see A is like the red, the red set, and B is like the blue set. But you see those are actually, so A is part of B. So for example, if you have 1, 2, 3, 4, 5, and you have 2, 3, 4, then of course 2, 3, 4 is part of 1, 2, 3, 4, 5. So if this here is A and this here is B, A has not every element is the same, because clearly B has 1 and 5, for example, but A contains like the same elements than B, but not as many, so they're not equal. But yeah, A is a subset of B. Yeah, let's say you have 4 apples and your neighbor has 2 apples, and yeah, I think the idea should be clear. I don't need an apple example. Yeah, I'm sorry. So if A is not contained in B, then A is not part of B, and now it's really, really important. It could still mean that there are elements which are equal. Yeah, let's say for example, what are we going to take? Let's say 1, 3, and 4, and B is 1, 5, and 6. Oh, I'm sorry. 1, 5, and 6. We already are seeing they have one element which is the same, but they are not like a subset. So you can't say B is a subset. But you could say 1 is an element of both sets. This is possible, but mostly you don't really, if you're a set theory, okay, you need this. I'm sorry, you need this sometimes, but for our understanding right now, what is important, if there is at least one element in A which does not lie in B, A is not a subset of B. Let's try to understand those relations with some examples. We know all natural numbers, the set of all natural numbers is actually a subset of all real numbers. I mean, all natural numbers are 1, 2, 3, and all real numbers are 1, 2, 3, 3, and so on, or 2. So you see, natural numbers have all the elements which are in B, right? Not all the elements, I'm sorry, but you understand, I'm sorry, since English is not my native language, I sometimes have some struggles with saying the right things. But I hope it's clear. So 1, 2, 3 is an element of all natural numbers. Therefore, 1, 2, 3 is also, this logic is very important. 1, 2, 3 is therefore, since it's a subset of the natural numbers, also is a subset of all real numbers. So 3 is a subset of natural numbers. 3 is a set with one element. So we can have the relationship, 3 is an element of all natural numbers, and 3 is an element of the set 3, since 3 just have one element and it's 3. Yeah. Quite obvious, but mathematicians always like to state obvious things, so maybe you need this. if we have A is a subset of A, and this also can mean that A is equal to A, which in this case is true, because A is equal always. If you have like stated a set A, yeah, you see A is a subset of A. So the relation, this relation signs of subset includes the equality of two sets. The equality, yeah, that's correct. So every set A, not every, but for you it's important to understand the empty set is a subset of every set. Okay, I believe there are some weird sets which don't have an empty set, I'm not sure, but generally speaking, an empty set is a subset of every set. Okay, now we get like to our two things I talked in the beginning. Let's go back here. We have well determined and well differentiated. So we also can say distinct. I'm actually not sure which is more correct. So well defined. Let's take houses as an example. They all possess properties that are characterized, which are characterizing the same thing. For example, if we have a look at a city, we can characterize houses with certain descriptions. So we are able to do a set with all houses in a city, but they are also distinct. So they are different. So all these houses, for example, have different house numbers, or not all have different colors, but some have maybe white, some are white, some are black, whatever. So there are differences between those elements. This is important if you try to determine, if you try to describe a set, a given set. Now I have a small thinking exercise, and this is the relation between sets. So what I like you to do is just pause the video, have a look to M1, M2, M3, M4, and M5, and have a look what are the relations between M1 and so on. One advice: always try to have a look what are the biggest sets and what are the smallest sets, and then try to have a look to the others, but make a bit of structure if you do relations of sets. So welcome back. So I wanna show you a little trick to prove, especially if you work with larger sets, if you missed one subset. So there's a rule, and I'm going to maybe eventually I'm going to make a proof. So every set with n elements, which and the set is not infinite, but instead finite, has two and an exponent n subsets. Okay. So, for example, in this case, we know we have three elements. Okay, element 1. And 1 and 2 and 3. Sorry, this is an n, m. So we've got three elements, and we are just going to do this here, up here. So we know we have 8 subsets, and we already can prove our results, our solution. I'm going to prove this because this is actually very easy and nice proof for beginners. So if you want to prove this, you just can try it, write a comment, and I'm going to say you if you are at least on the right track or not. But I'm going to prove this maybe in future, sometimes. First subset, of course, is the empty set. You don't have to make this, you just can make this. So then we start again, smallest to biggest. So 1, 2, 3, 1, 2, 3, 2, 3, and of course 1, 2, 3. Let's see if I missed something. 1, 2, 3, 4, 5, 6, 7. I missed one thing, and I know which one is. This is 1/3. I'm sorry. Now we have 8. This is the reason why I think, because you miss very easy some things. So those are all our subsets. 8 subsets. The second exercise is a bit more challenging. This is the last exercise. You have those sets defined here. So 0, 1, 2, 0, 1, 0, 1, 2, 1, 2, and x. This, and you want to find as many you want to find the essential relations. So just pause the video and see if you can come up with a solution. So we'll come back. So let's start with this. So obviously D has two solutions, 1 and 0. The reason for this should be quite obvious. 1 squared minus 1 equals to 0, and 0 minus 0 equals to 0. Yeah, and I believe there are no more relations. So what we can already see is that B and D are equal. So you see this has 1 and 0, and this has 1 and 0. We can see B equals to D. Let's find another relation. Let's have a look to C. C is our biggest set. We see this has 0, 1, and 2. A has 1 and 2. So we already can say A is a subset of C. Yeah, no, it's getting a bit comfortable. Let's make this so it's clear. And we know B is also a subset of C. And that's it. Like, those are our 3 relations. Nice. Thank you very much for watching this video. As I said, check out the blog if you want to study a bit. If you watch those videos once every day and really try to understand those, you should be able to prepare yourself pretty good for your university. But it takes time, so don't push too much. Bye.